11. Negation quantifier elimination rules. Earlier in the chapter, I promised 6 rules, and now we have 4 of them. The remaining 2 are tilde existential out and tilde universal out. As their names are intended to suggest, the former is a rule for eliminating any formula that is a negation of an existential formula, and the latter is a rule for eliminating any formula that is a negation of a universal formulas. These rules are officially given as follows. Tilde existential out. If a line of the form VFV is available, then one can infer the formula VFV. Tilde universal out. If a line of the form VFV is available, then one can infer the formula VFV. Schematically, these rules may be presented as follows. OVFV. VFV OVFV. VFV. Before continuing, we observe is that both of these rules are derived rules, which is to say that they can be derived from the previous rules. In other words, these rules are completely dispensable. Any conclusion that can be derived using either rule can be derived without using it. They are added for the sake of convenience. First, let us consider O, and let us consider its simplest instance where Fv is Fx. Then O amounts to the following argument. Argument 1 x Fx. It is not true that there is at least one thing such that it is F. Therefore, x Fx everything is such that it is not F. Recall from the previous chapters that the colloquial translation of the premise is nothing is F, and the colloquial translation of the conclusion is everything is un F. The following derivation demonstrates that argument 1 is valid, by deducing the conclusion from the premise. 1 x Fx pr2 x Fx ud3 fa id4 fa as5 dd6 x Fx 4 I7 1 6 I. Next, let us consider O, and let us consider the simplest instance. Argument 2 x Fx. It is not true that everything is such that it is F. Therefore, x Fx there is at least one thing such that it is not F. Recall from the previous chapter that the colloquial translation of the premise is not everything is F and the colloquial translation of the conclusion is something is not F. The following derivation demonstrates that argument 2 is valid. It employs lines 1, 5, 11 a seldom used sentential logic strategy. 1 x Fx pr2 x Fx id3 x Fx as4 dd5 x Fx ud6 fa id7 fa as8 dd9 x Fx 7 I10 3 9 I11 1 5 I. In each derivation, we have only shown the simplest instance of the rule, where Fv is Fx. However, the complicated instances are shown in precisely the same manner. We can in principle show for any formula Fv and variable v that VFV follows from VFV, and that VFV follows from VFV. Note that the converse arguments are also valid, as demonstrated by the following derivations. 1 x Fx pr2 x Fx id3 x Fx as4 dd5 fa 3, 06 fa 1, 07 5, 6, I1 x Fx pr2 x Fx id3 x Fx as4 dd5 fa 1, 06 fa 3, 07 5, 6. I. Note carefully, however, that neither of the converse arguments corresponds to any rule in our system. In particular, there is no rule tilde existential in. There is no rule tilde universal in. The corresponding arguments are valid, and accordingly can be demonstrated in our system. However, they are not inference rules. As usual, not every valid argument form corresponds to an inference rule. This is simply a choice we make. We only have negation connective elimination rules, and no negation connective introduction rules. Before proceeding, let us look at several applications of O and O to specific formulas, in order to get an idea of what the syntactic possibilities are. 1 x Fx. X Fx 2 x Fx and gx. X Fx and gx 3 x Fx and y gray are xy. X Fx and y gray are xy 4 x Fx. X Fx 5 x Fx gx. X Fx gx 6 x Fx y gray and are xy. X Fx y gray and are xy. Having seen several examples of proper applications of O or O, it is probably a good idea to see examples of improper applications. 7 x Fx y gy wrong. X Fx y gy 8 x Fx x gx wrong. X Fx x gx. In each example, the error is that the premise does not have the correct form. In 7, the premise is a negation of a disjunction, not a negation of an existential. The appropriate rule is O, not O. In 8, the premise is a conditional, so the appropriate rule is O. Of course, sometimes an improper application of a rule produces a valid conclusion, and sometimes it does not. 8 is a valid argument, but so are a lot of arguments. The question here is not whether the argument is valid, but whether it is an application of a rule. Some valid arguments correspond to rules, and hence do not have to be explicitly shown. Other valid arguments do not correspond to particular rules, and hence must be shown to be valid by constructing a derivation. Recall, as usual, inference rules apply exclusively to whole lines, not to pieces of lines. It is valid, so we can derive its conclusion from its premise. The following is one such derivation. It also illustrates a further point about our new rules. Example 1 xfx xgx pr2 xfx xgx cd3 xfx s4 xgx id5 xgx s6 dd7 xfx 1 5 08 xfx 7 dn9 far8 010 far3 011 9 10. This derivation is curious in the following way. Line 4 is shown by indirect derivation, rather than universal derivation. But this is permissible, since ID is suitable for any kind of formula. Indeed, once we have the rule O, we can show any universal formula by ID. By way of illustration, consider example 2 from section 7, first done using UD, then done using ID. Example 2 done using UD1 xfx gx pr2 xfx xgx cd3 xfx s4 xgx ud5 ga dd6 fa ga 1 07 fa 3 08 ga 6 7. Example 2 done using ID1 xfx gx pr2 xfx xgx cd3 xfx s4 xgx id5 xgx s6 dd7 xgx 5 08 ga 7 09 fa ga 1 010 fa 3 011 ga 9 10 012 8 11. Now that we have O, it is always possible to show a universal by indirect derivation. However, the resulting derivation is usually longer than the derivation using universal derivation. On rare occasions, the indirect derivation is easier. For example, go back and try to do example 1 using universal derivation. We conclude this section with a derivation that uses O in a straightforward way. It also involves relational quantification. Example 3 1 xyrxyy rix pr2 xyrxy pr3 xyrxy dd4 y ray 2 05 y ray y re 1 06 y re 4 5 07 y re 6 08 rba 7 09 yrby 8 I10 xyrxy 9 I